Okay, chapter 23 is on electric current. So, when the ends of an electrical conductor, like a metal, are at different electric potentials, charge flows from one end to another. So here's an electric conductor, a wire. This end is held at a higher electric potential, the plus end, and this end is held at a lower electric potential, that's the minus end. And so there's this motion of charge, electric charge, going from the plus towards the minus. So there's a very useful analogy, which is that if you have a high electric potential and you have a natural flow of charge to low electric potential, that's like water flowing from a high pressure to a lower pressure. Okay, so this pipe carries water from the high potential to the lower pressure, and this wire carries charge from the higher potential to lower potential. So continuing with this analogy, if you want to maintain current flow, you need a battery constantly providing a potential difference, and that's called a voltage. Analogously, if you want to maintain this water flow through this pipe, you need to keep adding water here, keeping a high pressure on this end, and pulling the water out of here, keeping a lower pressure. You need a pump to do that. So a pump is analogous to a battery to keep the flow going. Current. So when charged particles move, they transfer electric charge from one place to another. That's called electric current, or just current. And a conductor is a material that has some free charged particles that can move around. For example, in a metal, negatively charged electrons can move around inside the metal, while the positive nuclei remain fixed in that lattice. Okay. Certain types of solid semiconductors have positively charged electron holes which can roam around inside the material. And in liquids, there can be ionic liquids where there's positive or negative ions which can move around inside the liquid carrying current. So current is a number. Electric current is the rate that charge moves from one point to another. The symbol is I. So if a certain amount of charge, delta Q, moves through this light bulb every amount of time, delta T, then you divide delta Q by delta T, that's the current. Charge is measured in coulombs, time is measured in seconds, so the unit of current is coulombs per second. And we have a special name for that, it's called the ampere. 1 coulomb per second is 1 amp, with the letter A. Voltage is also a number. Electric potential difference is the same as voltage. So you have a high voltage here. A plus terminal of a battery is at 1.5 volts. The negative terminal of the battery is at 0 volts. So there's a voltage of 1.5 across this light bulb. If it was no voltage, there'd be no current. And the unit of voltage is volts. So 1 volt turns out to be equal to 1 joule per coulomb. So what we say is that when a voltage is set up across this light bulb, then the current flows through the light bulb. How does battery work? Well, energy is stored inside a battery in chemical bonds, and when current is flowing through the battery, it disintegrates zinc or lead in this acid, and that adds energy to the current. And then that current has some number of joules per coulomb in it, which get used up in a resistor like a light bulb. So resistance or current in a circuit depends on voltage and resistance. So a resistor is a circuit element. These are all resistors that use up energy somehow. Either they might make light or sound, or they might just create heat. And no matter what they are, in a circuit diagram, you just draw a resistor as a squiggly line. Resistance is also a number. When you apply a voltage across this light bulb, the amount of current that flows through it depends on the resistance, measured in ohms. The symbol for ohm is omega, the capital Greek letter omega. And 1 ohm is 1 volt per amp. Turns out that the higher the resistance of the object, the less current will flow through it for a given voltage. Some factors that affect the resistance of an object is what it's made out of. Rubber has more resistance than copper. Its shape, so its cross-sectional area. Thin wires have more resistance than thick wires, and longer wires have more resistance than shorter wires. Ohm's law states that the current through an object varies directly proportional to the voltage across it and inversely proportional to the resistance of the object. So in symbol form, it's I equals V over R. So for example, if you have an object with some constant resistance, you double the voltage, you'll double the current. If you double both the resistance and the voltage, the current will remain the same. You are a resistor, so the human body has some resistance, which depends on what the exact path is of the electricity through your body and whether your hands are wet or dry. So if your hands are kind of sweaty, the resistance between your two hands can be as low as 500 ohms. So imagine you were to grab two broken light bulbs, and at some moment this was at plus 120 volts and this one was at 0 volts, grounding you out. That would be 120 volts going across your body. And if your resistance is 500 ohms, you can use Ohm's law to solve for the current. Is 120 volts divided by 500 ohms is 0.24 amps. And that'll go right through your heart, which is not a good thing. Electrical current in your body can cause tissue damage and can also interfere with the beating of your heart, which is an electrical process. And also, it really, really hurts to get electrocuted. So I want to talk about the direction of electron velocity in a metal wire. So what happens when you flip on a switch? What happens is that establishes an electric field inside a metal wire. So ordinarily, electrons are moving all around and randomly bumping against atoms and other electrons like they would in this dashed line. Well, once you set up an electric field, then this electron, as it's moving, is always being nudged away from minus and towards plus. Okay? So that motion drift of all these electrons is what we call the current. Actually, we've defined the current as always going from plus to minus. That's the flow of positive charge. But in reality, in a metal wire, the drift of velocity of these tiny electrons is actually in the opposite direction. So that's something to keep in mind. DC versus AC. So direct current means that the current is flowing through a wire in one direction only, from the plus to the minus terminal. Alternating current is when the current is going back and forth with time. And this is accomplished by actually alternating the polarity of the voltage, so plus minus plus minus. And in North America, all of these power outlets have 60 hertz, plus to minus, and the voltage is 120 volts. Now you can note that power transmission is more efficient if you have higher voltage. So across the Atlantic Ocean in Europe, they tend to use 220 volts as the standard. That's a little more efficient than Canada and the US, which continues to use 120 volts just because so much equipment is already installed using 120 volts. It's historical. And it's good to note that your laptop or your cell phone uses DC, so you need a converter when you plug in your laptop or your cell phone, which converts AC in. And there's little diodes in here, which are little one-way valves, which only allow the current in one direction, so you get DC out. Power. Power is the rate at which electricity is used up in a circuit. The equation for power is current times voltage, P equals I times V. The way the units work out is current is measured in amperes, and voltage is measured in volts. An amp is a coulomb per second, and a volt is a joule per coulomb. So when you multiply, the coulombs cancel, and you get joules per second, which is watts. For example, you can solve that if you have a 100-watt light bulb, solve for a current, and the voltage is 120 volts, the current through the light bulb will be 0.8 amperes. So circuits can be connected in two main ways: series, in which there's a single pathway for the current, and parallel, which there's branches, in which the current can flow simultaneously through different paths. So a series circuit has electric current going through one pathway, and the total resistance to current is the sum of these individual resistances. So here's the plus terminal of a battery, here's a switch, and all these three light bulbs are connected in series. And so if one of these bulbs breaks or a switch is open, then no current will flow. A parallel circuit is hooked like this. So here's the plus terminal of the battery. Here's the negative terminal of the battery. Each one of these light bulbs is connected directly to the plus and also directly to the minus. And the current splits up across these different branches. Right now, this light bulb is, I guess, broken, or the switch is open. There's still current that can flow through these two light bulbs and get to the minus of the battery. So a break in one path does not interrupt the flow of charge through the other paths. Sort of analogous situation for parallel circuits is lineups at the grocery store. Okay, so it takes time to get through each lineup, but as you add more lineups, the lower total resistance of the circuit, since you can go through these different paths. And if one path breaks, if you've got a price check on one aisle, then people can continue through the remaining paths. So that's why homes are always wired in parallel. So here's the line through your house. You've got 20 amps going this way. Some, maybe 2 amps will go through a lamp, 10 amps will go through a heater, 18 amps go through a toaster. And so that adds up to the total power through this line. When the current through a line is excessive, overheating can result in a fire, which is why we have circuit breakers. A circuit breaker is an automatic switch that turns off when the current exceeds a certain value. And this can prevent fires from occurring. So unlike a fuse, which burns out once it operates once, a circuit breaker can be reset multiple times. So here's a bunch of switches in the basement of my house, each one set to flip off if the current through the line exceeds a certain amount.